Okay, welcome to the 372 tutorial for Lab 4 of the Stress Concentration Lab. For this lab, the dimensions and the material and everything are completely up to you. You are trying to verify the stress concentration table in the book, and that you'll do some math that I'll show in the lab in order to find the KT value, but it's all independent. I mean, you can model whatever material and whatever dimensions you want as long as you do your math correctly to get the right KT values. So at this point in your ANSYS education, you should be able to do a lot of this on your own. So I'm actually going to model, rather than model this shape from the figure in the book, I'm going to model this shape here. So rather than one hole in the center, I'll have two holes in the center, and I'm going to apply my force in a different direction. But you should be able to take those tools that you learned from this model and apply it to making this model, which will be a different one. But you should be able to figure it out on your own. So for the parts that you already know, I'll go quick and I'll slow down for the new things. So add in an element type. Yes. Okay, so we're going to use a solid element because we are creating our own custom 3D volume, pretty much like a CAD program. So we're going to use this brick 89185, and it's a solid element. Material properties, this is nothing new to you guys. Again, you can use whatever material you want, but I'm just going to stick with basic steel. Make sure to include your density. So modeling this is where the new stuff comes from. We're actually going to go into model and create, except this time instead of key points and lines and stuff, we're going to create a volume. Or we're going to create, areas, and then we'll extrude that area into a volume like in a CAD program. So we're going to create an area. Basically, we want to create this shape here. So we're only going to model a quarter of this plate. And because the lab says reduce the model by drawing a quarter of the plate in ANSYS and use symmetrical BC. So I'm going to model only a quarter of this. And we want to end up with basically this, only this shape here. So to start with that, we're going to create a rectangular area by two corners in Z. So now we can pick one corner and then pick our width and our height. So I'm going to have it at the origin. And then for the width and the height, I'm going to actually use variables, which I haven't yet showed you how to do, but they're very useful. So I can set parameters in ANSYS. I'm going to hit cancel just for now. I can hit set parameters in ANSYS, and then if I want to change the dimensions of my model or change the amount of the load, I can just go in my session editor and change these parameters that I set, rerun my code, and ANSYS will solve the model with the new updated geometry and new updated loads. So in your command prompt up here, you just type in the variables you want. W, width equals whatever, 10, height equals 5, and then I'm going to draw a circle later, so I'll have radius of 1. Basically, you can type in any variables you want to use here. If you want to type in Fy equals 1,000 pounds or 1,000, feel free. Anytime you have a field in ANSYS that you want to plug in a number to, you can use a variable instead. So when I draw my rectangles by two corners, I'll have my point at the origin. I'll have a width of W and a height of H. And okay, and there's my rectangle. I'm going to need to draw some circles as well in order to finish this shape here. So I want my circle halfway up the length, or halfway up the height of my rectangle. So when I choose create area circle solid circle, my center will be 0 in X and H over 2 in Y. So it's halfway up my shape here and the radius of R. So there's my circle. And now I want to subtract this circle from this rectangle and leave that as a cutout. So this is under modeling, operate, and booleans, meaning like add and subtract, or divide, that kind of thing. Anyway, I'm going to choose boolean subtract, and then I'm going to subtract, these are areas. So the way this works is that you first select the shape that you want to keep, like left click, then hit OK. Make sure you hit OK, and then left click the shape you want to cut out, and hit OK, and then it cuts out the circle from the square. So so basically the way to think of it is click the shape you want to keep, and then click the shape you want to delete or remove. So that's now we need to extrude this area into a volume. So I'll operate extrude and an area along a normal. So basically at normal to the area, I'll create a volume. So then I'll click the area and hit OK. And then the length of my extrusion is how thick I want it to be. I should have used a variable t here because we might not want to vary that in the future. But I'll just have it be 1. So now if you right click or control and right click to rotate, you'll see that we have a full 3D shape here. So that is the end of our modeling. Meshing is also new here. First, the attributes are the same actually, but we'll select a volume and we'll tell it to be material number 1, which is at basic steel, and then hit OK. So now ANSYS knows what the blue block is, and then size controls is going to be all new for this solid element here. So we're going to use this mesh tool for this, which actually kind of does the meshing for you, but it kind of picks its own. Kind of picks its own grid, I guess you could say. You don't have much control over whether a certain area has a finer mesh than another. So what we're going to do is actually tell ANSYS to make certain areas at a finer mesh than others. So we're going to go into size controls like normal, manual size, and this time we're going to do it for an area. We're going to pick certain areas because I want to know more accurately the stresses along the inside of this circle, because that's our stress concentration. So when I pick these areas, I can tell ANSYS to mesh them fine, and then the mesh tool will do a generic, less refined mesh for the rest of the shape. So I go and left click and select all the areas that I want to make a fine mesh. So hit OK, and I'll pick an edge length here for all those areas. So when I hit OK, so I'll pick 0.1. Each edge should be 1/10 of an inch. I'll hit OK. And now ANSYS knows to make those areas in a much finer mesh than the rest. So back in this mesh tool, if you want to make your entire model a really fine mesh, you can turn on Smart Size and drag this down to the fine option. So that's an option for you if you want, but I want the rest of this model to be kind of a wide mesh, because I don't really care about the stresses over there. I just care about them in this circle. So therefore, I'll dedicate all of the computing to the important parts, so it doesn't take as long to solve. These options here, it depends on your element type. Some elements like to be meshed with the tetrahedral element size shape. Some of them like a hexagonal element. Anyway, for this brick element, we're going to use hex and then sweep. So a mapped mesh, it takes like a square grid and pulls it through your shape. But these brick elements don't like that. Anyways, sorry to go over your head. We're choosing hex and sweep here. Then when we hit sweep, it does all our meshing for us. So I'll pick this volume to sweep and hit OK. And you'll notice that back here where we don't care about the stresses, we have larger elements, so we have less computing power going there, and all our computing power is being dedicated to the point where we know the stresses are going to be greater, which is along this stress concentration here. I probably could even ignore this side as well and just had it mesh these areas fine. So that's all the meshing we've done. Now we just need to do our loads. So usually you lock down a key point, but we're actually going to do a symmetry boundary condition. So let me show you how to get to that. Loads, define, apply, structural, displacement, just like usual. Except this time, instead of doing on lines or anything like that, or on key points, we're going to do a symmetry symmetry boundary condition on an area. So what this does is it tells ANSYS to mirror everything in the model along this area. So I'll pick this area and these two, and hit OK. So now, anything I apply to this model, it will be mirrored along those areas. So if I apply a force on the right, it'll be mirrored basically as a force on the left. So this way I only have to model a quarter of my plate. But I still need to apply that load on the side. So for the demo, I'm going to apply the load up on the top, but we're going to use a pressure, because in the stress concentration table, it's basically assuming that you're pulling on the plate laterally on the sides, and to make that an even pull, I guess we're gonna do a pressure on an area. So we're going to evenly pull along all sides, or along the whole side of the plate. So pressure on areas. And you'll pick the area you want the pressure to be on, and hit OK. And then you'll just give it a pressure value. And so in ANSYS, the default for pressure is always into the shape, because if you think about pressure, it's usually pressure on an object. So if you want to pull on the plate, we need to put in a negative value. So again, you can choose whatever pressure you want here. You'll do your own calculations to find your KT value. But just to make it easy, I'm just going to put 1,000 PSI. So hit OK. And the red lines mean that there is a pressure on that area there. And so now, believe it or not, we have almost everything we need to solve this model with. I haven't constrained anything in the Z direction, if you've noticed. So ANSYS will want that. So if I do a displacement on an area, I can just pick this area, either one on the side, hit OK, and tell it to constrain in the Z direction. So now this plate can't slide in the Z direction at all. So we have a properly constrained plate, because we have, I guess theoretically, we have the X and Y direction constrained with that boundary condition. Because if you have a force on the left and on the right, that net is 0. So we have basically a force and a reaction. And then in Z, I've constrained it as well. So I can now run my solution. As you can see, solid shapes take a lot longer to solve because there's a lot of 3D meshing going on. So I will tell it to graph. It's the same thing as before. Plot results, contour, nodal solution. And I want to choose stress and von Mises again. And hit OK. And here you go. I have all the pretty colors and all my stresses plotted out. And so we can see that, as expected, the greatest stress is in that stress concentration, in the cutout there, and it's 3.19 KSI. So I would take that value, I would use the calculations in the book and find a KT value and plot it. And then if I want to iterate on my model, I go to the session editor, and I can change any of these parameters here that have star set. I can change any of those I want. So if I want to make my hole a lot smaller, I'll make it a quarter of an inch, let's say. And then I hit Control A, copy my code. So Control A, Control C, and then I can paste it into the command prompt to rerun my code. And as you can see, it's already updated the size of that hole because I changed that parameter. And now if you wait for it to solve, all right, it'll replot for us, and we can see that our stress is smaller. That may seem confusing at first, because you would believe that with a smaller circle, it's a smaller radius, and therefore the stress concentration should be larger. And it is, but you'll see once you calculate that, because this area right here is a lot larger, that smaller number actually makes sense. Anyway, when you do the math, you will get a larger KT value. So basically, you'll have to go in your session editor and iterate the size of that hole a few times to get a couple different ratios. And this will all make a lot more sense when I go over the lab. And anyway, the easiest way to iterate is just go to session editor and change those parameters that you have. So that's all you need for this lab. So good luck.